Welcome. I thought this morning a little bit more about the Morse Sard theorem in the discrete, something I worked on a couple of years ago in graph theory. So the classical theorem is very nice, and it's something we also see in calculus. If you have a function on a manifold and you look at the level surfaces, they are in general manifolds. So here there's a critical value, a critical point, which is a saddle point. So the level surface is not a manifold, but in general it's a manifold. So if you look at, for almost all values, the level surface is either empty, if you are out of the range, or it is a hypersurface. And if you have two functions, that's in general it is a codimension 2 surface. And so that's how I thought about this. And actually Anthony Morse, it's not the Morse, from Morse theory, Anthony Morse was in the war 1939, proved this theorem for n equal to 1. Sard was a couple of years later generalizing it to arbitrary dimensions. I formulated it in such a way such that it's identical to what we have in the discrete, what we can prove in the discrete, but in the discrete there's a miracle. This almost all which we have in the continuum disappears. So what will happen is for all, it's kind of strange, a strange behavior in the discrete. It's kind of all the singularities somehow disappear. So how I thought about this here in this graph theoretical setup, that we have a coloring, meaning that if you have a graph and you have a function on the vertices, that the values at connected vertices are different. That allows you to kind of look at all the simplices on which the color changes. So kind of some, say if you have a f equal to 0, so we look at the places where f is negative, look at the places where f is positive, and then there are places where the sign changes. So these are simplices. Of course they don't contain zero-dimensional simplices, so it's actually not a simplicial complex, it's a delta set. I'm a big fan of delta sets because it's a topos, you can do anything there. And it's a very, very natural framework. So what we have here now, one-dimensional and two-dimensional objects, but the one-dimensional objects actually correspond then to the zero-dimensional object in the graph. So you build a graph where the vertices are just all these simplices where the function changes sign, and then you build a graph, and this is in this case a one-dimensional graph. So that was actually kind of the situation. If you have a two-dimensional, this is a two-dimensional sphere, the icosahedron is a two-dimensional sphere, and if you take any coloring on the vertices of this icosahedron, you have unions of one-dimensional curves, closed curves, which are circles. Or it's empty, kind of if you are outside the, like here, when you are outside the range, if the value is outside the range, then of course the inverse image is empty. I was then also looking, kind of thinking like an algebraic geometer. You look at several functions, and then you look at the points where both functions satisfy the equation. So that's like two polynomials. And so what happens in this case, and that was kind of something which vexed me a little bit, that if you start looking at the f, the first function, the level surface of the first function, then you have a surface in the first barycentric refinement, and then you can look at the second function and then again apply this theorem, and then you have a surface in the second barycentric refinement G2. Now if you turn things around and you take first f2 and then f1, you don't get the same thing. right? So this is non-commutative. Somehow I didn't like that very much. I thought about it, and this morning I actually thought, why not actually just take the framework which we have in the continuum and kind of just take everything kind of one-to-one. So instead of having here real value, we just take another graph, another simplicial complex. All this works also for delta sets, so simplicial complexes, but graphs. For any of the delta set, you have automatically a graph, right? Graphs are very, very intuitive. You just take every set in your delta set is a vertex, and you connect to if one is contained in the other. Or, in the delta set case, you have a face map which tell you what is contained in the other. So graphs are very, very powerful, and not just one-dimensional simplicial complexes, but as powerful as the topos of delta set. This is the old version. I kind of reformulated this now in a way so that it looks exactly like this. So we have a graph, we have two graphs, G and H, you can call it M and N, finite simple graphs, and they are assumed to be M manifolds and N manifold. A manifold is a graph such that every unit sphere is a hypersphere. So in the case of the icosahedron, every unit sphere is here a C5 circular graph. And so this is what a manifold is. And then you have the notion of simplicial map. That's something which is a type of smoothness. So if you look at continuous maps in the Alexandrov topology, I worked the whole year on the first half of the year on these discrete topological frameworks, which is very natural, where this Alexandrov topology of a simplicial complex or a graph. You can look at this topology, and then continuous maps are, in general not simplicial maps. And then we have also a generalization of the coloring. What you can think about this is this, that you have a coloring means that if you have you take a one-dimensional simplex, this is mapped into a one-dimensional simplex, or a two-dimensional simplex is mapped into a one-dimensional simplex, right? You don't have the possibility that an edge is going to a point. If it is going to a point, this means that the values would be the same here, and that would not be a coloring. So that assumption which we assume here, that the kind of simplices are just not collapsing in a crazy way, is kind of a coloring assumption, and that's you can think about this also as a smoothness, part of the smoothness condition. Then we have for every simplex in N in the target, we have that the inverse image is M minus N manifold or empty, and so that generalizes the case when we map into a one-dimensional simplicial complex. Target is one-dimensional, but it can be arbitrary dimension. And then this problem here disappears with the commutativity. So we have now, if we map into a two-dimensional complex, then we have surfaces which have codimension too. Now the proof is essentially the same than what we have done here. The key is to see in a simplicial complex that you have the unit sphere. If you look at the unit sphere of a point, if you take an edge and you look at the unit sphere of an edge, these are all triangles which contain the edge. This is S plus, and you have all vertices which are contained in the edge. This is S minus. In a simplicial complex, we have that every unit sphere is the join of S plus and S minus. S plus are all the simplices which contain the simplex, and S minus are all the simplices which are inside the simplex. And the join is because they are all connected with each other, right? So you connect every vertex of S plus with every vertex of S minus. This is the join. And so these are spheres. So this doesn't involve yet the map F at all. This is true for every simplicial complex or graph with a simplicial complex which comes with a simplicial complex. And then we are looking at the inverse, the inverse F minus 1 y, which is K. And now we look what happens with the unit that it's a manifold. We have to show that this is a sphere. Now what happens is with S plus nothing happens because of this condition, of this simplicial map condition. We have also that S plus G is S plus K. What happens is in the S minus, in the simplex itself, there we have a shift in the dimension, and this depends on the dimension of the target. So we just get a minus n in each case. So we get the minus n here, so we get the minus n here, and then when we take the join again, we actually just shift also the dimension of the sphere SG sphere down to the sphere SK. It's very, very nice. It's actually even more transparent than in the case when we just think about graphs. So this is very fresh, and I have still to kind of also look at examples and illustrate this, but it's a nice framework how we can generate new manifolds from old manifolds, and that was the also original motivation of Sard or Morse, right? If you look at level surfaces of functions, you want to know when you have a manifold, and this is generically true that we have a manifold. That's it for today.